Welcome to graph theory, suckers. In one sense, this course is thoroughly outside my field of expertise. This was developed by Dr. Atkinson, who left here before Dr. Burns got here. So it's been a while. It was his PhD research topic, and I've learned a bit since then. It's only my third time through this. So you might catch me on some things, and that's a good thing, because I'll learn more, you'll learn more, we'll be all better together. You've seen all this crap before. My office hours are Monday, Wednesday, Friday, 12:30, 1:30 in the Enrichment Center, Tuesday, Thursday. Tuesday it's 1 to 3:30, Thursday 2 to 3:30. Come bug me. We're going to use Chartrand and Zhang graph theory. This is a fairly good, deep book. There's a lot more theory in here than I think is necessary, so we're going to skip around a bit, and there'll be some places where I bring stuff in from other texts that is a little more applied. To that end, this was on the recommended list, the Shams outline for graph theory. There are hundreds of problems completely solved in this. Wouldn't be a bad thing to hang on to. This is almost always a course that you're in for one of two reasons. It's a major requirement, it's a major elective. I don't expect anybody being here because, ooh, this sounded cool. I don't know, maybe. But most of the time, the prerequisites are enough to scare everybody else away. So, standard set of math learning objectives. We're going to do a lot of stuff. And in one sense, this is nothing more than patterning, pattern recognition. In another sense, it's the development thereof. Please don't get sick. I know everybody keeps telling me COVID is rising. Over the weekend, I got an email that one of the professors in the business school is already out. So you never know. But we're not doing on-campus testing. You're responsible for your own testing. And I'm doing the same thing I did last year. I'm recording everything. I'm scanning all the pages. If you're going to miss, you can catch it up. If I'm going to miss, I'll be doing this from home. But I don't want to get sick. So we're going to keep at it. Come to class. It helps, I believe, really. If I could just upload the book to your brains, we'd be done. I'd go home, have a beer. It's not going to happen. Every section has a homework assignment. There is a complete list thereof on our Canvas page. It's usually due 2 days after the completion of the stuff is that there will be periods later, Friday following. Tag you can, if I change, I have to redo. There's a scan. It's use it. I upload all my all the previous classes, just one fewer than most of my classes. Homework scale notes. Almost all of this is looking at again. I do use email to respond in 24 hours. Usually not up right in the morning. Assignments. There'll be a bonus. in class. It's going to hesitate, because if you'll report any type. If you tell that shouldn't stop you. If you want to tell someone, you can call numbers. You see something, likelihood of an instructor groups reported up the chain. May or may not get knowledge. What happens after that point? What I know. That's it. I don't hear anything else ever again. If you are legal, please let me know, ideally by the end of next week. Cook will be glad to the system. What I need. If I upload this to you, that's like in the back of your head. We'd be done. But I can't learn. It means if you sit there, ask each other here to here. That hard. Why? In that, then you're textbook. Is not written by 3 other books. Class for you just let me. I will. This book is find the answer. That's like somebody else. The engagement of academic honesty is not, hey, What question this class is? Yes, sir. Subject of this first lecture, so let's go right into it. What we look at to define the visualization. Chapter 9, relational graphs. We do all these pictures of that. A graph is made of we start with a V. These could be these could be elements. They could be programming. I could not be anything. The subset of two. My second listing of the numbers 4, and my four, 2, 4, 2, 2, 3, and 4, 4. If we're talking about sub G, similarly with edges, the edge or E sub G. I cheated. I stole directly from you. But description is useful to me as nothing. Tell it what the is. When you hear the graph, take a picture of it. You and for the record, I can't at all. Any arrangement an edge, draw from doesn't matter. I mean, one visible. There's no. I could just goes from 4 to 2. There are I want to know if people or if people left 82, 83, 87. Figure meet when? only 7 total in that. How do I need a way, I probably off, but counting is not going to be an easy way through. Connected to one, then look at 2. Well, I them that way. Write them all down. I've got members and 30 committees. Going down in that, trying to schedule. We ended up seats. From a radical idea. So as if and only difference 2 values is that there. Set in my notes. Sense. subtract them, see if the result you get is 1. If it is, connect them. Is 2, right? Eight is the sum of n. I connect 2 and 3 because I get 5. And 5 but we had a map. We couldn't get than 15 here. And I have to take it 6 choose. The vertices. So if I have the number of vertices and the number of you can have a graph of 0, 15. You have. I gave you simply give you the vertices. Let's go to town. I've labeled vertices here numerically. Quite often, we give them letters. Characters for our vertices, and our vertices are usually indicated by 2 combinations. So if I had three vertices, create the edges by listing 2 pairs. The edge really doesn't matter. Post one other edge I can, and then I've run the opposite. That's all I could. You're connected. We're going to use the term adjacent. Talk about an edge vertex, different. But incident. Now you can have a graph of size 0, means you have no edges at all, right? An empty graph. You have to have at least one vertex. Why? Go back to the very first sentence I wrote down. A graph is a finite, non-empty set. I said it right at the beginning. You have to have at least one vertex. And yeah, there has to be something there. Even if I don't hang any edges off of it, there's got to be at least something. Some graphs are unlabeled. We are not required to label the vertices or the edges. It's a lot harder to tell what's what then. We'll find some ways to describe graphs that don't require us to have labelings. Questions? Same graph, right? Unlabeled versus labeled. The same graph. Yes? Is that the same graph? I just straightened it out. That's the worst part about this. Your picture and my picture might not look anything close to each other, depending on the way we choose to lay out our vertices and what we label what. This graph really only can be drawn a couple of ways, and they'll all kind of look similar, but that one doesn't look the same at first glance, but it is. So how do I quantify or even just name properly these different ideas? We'll get there. Questions? Chess, checkers, Go, board games, right? Positional games. What if I took a nice, simple board, two by two chessboard, 4 squares. I'm going to give you 2 coins. How many ways can you put the coins on the board that are different? Problem stats time. How many ways can you do this? How? But if I do that sort of setup, like I can put no coins on there, right? I got to put those coins on there. 16 is too many. No. 1 coin per square. It is. Why? 4 choose 2 would tell me which 2 squares I'm going to occupy and which 2 are going to be blank. And then I have 2 options for where I put coins down, right? So there are 12 possible arrangements. Let's make a game. You have 2 possible moves. You can take a coin from wherever it is and move it horizontally or vertically to an empty spot. Or you can switch the 2 coins, no matter where they are. 2 moves, right? Here's my question. If I'm looking at a board where, I don't know, S is here and G is here, what other layouts can I get to? If I move once, no matter which move I do, where can I go? Now, I don't expect you to have this game fully fleshed out in your head, but I will say, there are my 12 boards. So if I'm in this one, what could I get to? If I'm at board number 2, coin 2, C2, what can I get to? I can move a coin horizontally or vertically, or I can switch them. I get C4, C8, and C1. C1 moves the bottom coin, C4 moves the top coin, and C8 swaps them. So now I can take all 12 of these, make these my vertices, and make legal moves my edges. And all of a sudden, I've got a game. Here are the things I can move to. Here are the things I can't. Gameplay stops when no more moves are available. That isn't going to happen because I can always just switch the coins and switch back and switch the coins and switch back. And that's boring, but it works. And I end up with all of these different options available to me. Here's where I can move. This is a very small board, yes, with a very small number of pieces. There are 64 squares on a chessboard. There are 16 pieces, some of them with different move rules than others. Given a picture of a board and knowing whose move it is, white or black, what are the next legal boards I can get to? That's going to be a really big graph, right? Chess programs are 60 years old. Modern computing chess programs are 60. There are, quote, chess robots from the early 1200s, but they were really small people hiding inside boxes playing chess. But nowadays, I've got the ability to make a computer do this. And it can decide which of those next boards is most advantageous. And it can look further ahead, maybe 2 moves, maybe 3 moves, just looking at what the most advantageous moves are based on some scoring system that I build into each board. This is a good board, this is a bad board. This is a +2 or a -1. I could weight myself and assign additional information here. Even just simple games. Anybody play Wordle? How's it work? Tell me how the game works. And you have to find the right 5-letter word, yes? And you know whether your letter is in the right place, the wrong place, or is not involved at all, yes? There's an older version of this game that gave you the top word and the bottom word. And you had to change one letter in each row and go from one word to the other. So if I start with the word aim, and I only change one letter at a time, and it has to be a word in the dictionary, a 3-letter word, can I get to car? Yes. Aim. I can even go through a version that's not here. I can go from aim to air, right? See, but notice this has reversals as well, right? I switched 2 letters. They were in the wrong places. Aim to air. Oh, well, I might not be able to do anything after that, but I can go from aim to arm, art to act. I can get to car eventually. I can get there in a lot of different ways, can't I? Transformations as a graph. This is a traffic interchange. People are turning, people are going straight, all sorts of things are happening. There are still classes happening. Who's allowed to go when the light changes? Which lanes can go at the same time? Which lanes can't? I'm kind of really wanting to know that because I don't want to die at this intersection, right? So if I say, okay, lane 4 and lane 5 could move at the same time. But if lane 4 is moving, lane 7 shouldn't be, right? Because then there'll be a potential accident. Same thing with lane 4 and lane 1. So who moves when? Who's allowed to move? Who isn't? Well, I could say, okay, if I decide on who's not allowed to go at the same time, I can build a graph. I could build a graph of who is allowed to go at the same time. How would that graph compare to this one? If this is the graph of who's not allowed to go at the same time, it'd be all the rest of them, right? Every edge that is not currently on this graph are people that are allowed to go at the same time, because these are the people that are not allowed to go at the same time. And it's a yes-no question. I get together a pile of chemicals that I need to transport from the storeroom in Lynch down to the front driveway in Admin. What chemicals can go on the same cart, and what chemicals would be a bad thing if they were in the same car at the same time? I want to have another Ohio issue. Palestine should not be created on the lawn. What is it good for, then, is exactly the right question. Now, if I find the situation and can figure out how to abstract it, what do I learn from that abstraction? How many cycles of the light do I need to get every lane to go once? How many times will the light need to change? Can I do it in just 4? I've got some turn lanes in there, so probably not. How do I make it work? And this is just this one intersection. Do this in Greensburg. City of Pittsburgh. No, I don't want to do that. What do I do? Abstraction. What can I quantify? What can I make this work? I guarantee you, I could figure out the cycles of the light every lane to go at least once. At the very worst, I could just do the time, right? 9 individual lines. What do I do? Where's my balance? How do I assign balance to this? Allow me to calculate the right pieces. Now this visualization to start with. But now I have to say, okay, what can I build? One of these connections, like to be one way, or to be valued. There's more to this game. Where we I will tell you that one of the graph theory presentations I saw was on hydrocarbon. You take petroleum and you heat it at different of gas. Methane, propane, butane, isobutane is different than butane, and they all have slightly different boils. How do you build a distillation column that will add the pieces you want and only the pieces you want? Turns out the graph theoretic properties of hydrocarbons are really direct. And Kimber, now at Indiana University of Pennsylvania, and Whitehead, did research in that 90s. But it's still studied today. Given by the American Association of America, the Allegheny, of which we are a part, will be hosting a on propagation graph somehow. I'll send you this. Unfortunately, it's at 4 o'clock, which is all reading on campus happens. I can't be there, but I think you should. But for now, we'll see you all. Hope you have a wonderful rest of your day.